I'm here at the University of Hartford with my friend, Professor Gabe Herman from the Hart School, and he introduced me to my new friend, Dr. Jasinski, at the College of Engineering, Technology, and Architecture. As you can see, they've got some really, really cool facilities here, reverb chamber, an anechoic chamber, some other things, and you'll get to hear that in just a moment. But first off, can you help us understand what you and students here are up to?
Yeah, so acoustics is the study of sound and vibration, and we offer 2 degree tracks here at the University of Hartford. One is a Bachelor of Science in Mechanical Engineering with acoustics concentration, so coursework that relates to the sound and vibration of machines and buildings and structures. The other degree program is Acoustical Engineering and Music, which takes those same core courses and adds 40 credits of courses at the Hart School of Music. That's private lessons, ensembles, ear training, music theory, and music history. The idea being that our graduates are going to have full mastery of what they're hearing. So the sound study over at the music school trains your ears. The study here at the engineering school is going to be telling you how to interpret that, how to explain it to somebody who's building or designing a building or an aircraft or an automobile, helping them with understanding all the issues that are related to the sound and vibration of it.
So we'll take a look inside the anechoic chamber. It's odd when you go in, and just anechoic. It's not echoic. There are no echoes, meaning you pretty much only hear direct sound, right?
Exactly.
And we will take a closer look, but the way you achieve that is you're kind of standing on a net, and beneath you and on every side of you and above you, you've got acoustic treatment, but not only just any acoustic treatment, it's very, very deep acoustic treatment, right? Can you help us understand why that's the case?
Yeah, so in a typical room, recording studio, or maybe even a home office or a classroom, you might see 1 or 2 inch thick acoustic panels. Can take all sorts of different forms of colors and textures, but 1 to 2 inches is about as thick as you'll get. In a space like this, in order to actually reduce as much of the sound at the lowest frequencies you can, we actually have 2 feet of material. So all of the wedges that you'll see, floor, ceiling, and walls, as you mentioned, 2-foot fiberglass wedges that are wrapped in a silk fabric and covered with a small metal grate so that they keep their shape. Because the material, very important, that spindly material inside is porous, and that's going to absorb all of the sound, or as much of the sound as possible. It's actually converting it to a very small amount of heat, not enough that you could feel it on the material, but that's what our sound absorption is. But the shape is important too. The wedges really make it so that if you think of sound as radiating in all directions as rays, one ray is going to hit part of that wedge, and it's going to bounce into another wedge. So say you absorb 95% of all of that sound on the first hit, the first interaction with that material. Next one, that's going to be 95% of that. Now you're already talking about a very, very low amount of energy. And there's going to be quite a few of those reflections before sound comes back out. So you effectively reduce more than 99% of the total energy that goes into any one of those wedges.
Contrast that then to this other door number 2, which is the reverb room, right? That's all flat reflective surfaces, right? That are not angled. They're just, you said that you could achieve how long of a reverb?
So if the room is unoccupied, a reverberation time, which is about the time it takes from the onset of a sound until you can't hear it anymore, can be about 4.5 seconds. So a pretty long time for that to last and persist within a space. And so you'll hear, if you try to talk in that room, it's a little hard to understand what's going on. But yeah, you achieve that not just by increasing the size of the room, because the size does matter for what a room is going to sound like. You're in a big cathedral. That volume is part of what makes it so that the sound persists for a long time. But the materials are likely the more important component. These 2 labs are very similar in size. This one's a little bit larger, but it's really that the materials are about 95% reflective. So of all the sound energy that comes into any one point of that material, 95% of it or more is going to continue bouncing around, find another material, keep bouncing around. So it's really the opposite effect of what happens in that room, and that's what makes it persist for so long.
Can we say a little bit more about how the rooms are constructed? So they're not just rooms like connected to the floor. They're actually suspended from outside influence altogether.
Yeah, so I mentioned acoustics is both sound and vibration. And in those facilities, you don't want to just be acoustically isolated. And these are isolated by those interior materials as well as a double wall configuration with an air gap, but they're also vibration isolated. So actually in the back there, you might be able to see one of these coiled springs. Actually, maybe you want to grab, sure. Yeah, so this is an example of the type of mechanical spring that we actually have underneath both of these rooms. It's not so much that you'd necessarily feel the trampoline kind of effect, but during our renovations of this space, we actually were able to calculate the static deflection that we'd get from loading all of our equipment into that space. We had to put basically everything in our lab into that room while they were doing renovations, and it sunk enough to the point that this door was almost unopenable because of the deflection that you have from the loading of these springs. But this makes it so that you're vibration isolated from the room, the rest of the building rather. And part of the importance of that is that right through those walls over there is a loading dock. We're going to have big trucks coming in. That's going to cause a lot of low frequency vibrations. So whether you're doing a sensitive test or not, you really don't want to be feeling those vibrations. So yeah, sound and vibration isolated from the rest of the building.
Now, are these springs, this is something new to me. This seems like really next level, right? When I've seen other studio designs with things to address that sound transmission, I've seen things like a room within a room or air gaps between walls and things like that. Am I addressing all of the different methodologies?
Yeah, and it really is application specific. There might, if you're working in an environment where you don't need to isolate yourself from very low frequencies, this might be overkill. Room in a room is essentially what's happening here, where you've got everything set on here, and the technology is really fairly simple. Coiled spring with some known stiffness to it, and then a material that's going to add some damping. And we've got equations that we teach in a course of vibration sequences that the students know how much load this can handle, what kind of natural frequency this is going to have, because you also don't want to necessarily encounter resonance if you're adding an additional mass spring system. But in cases where you do need that kind of isolation, yes, seeking out those type of extra isolations or extra isolation technologies would be good. The other aspect that can be looked at is more of an active damper. This is something that's sometimes used for buildings or even ships at large scale, where you've got a vibration that may be happening at a pretty large scale due to seismic activity, wind conditions and variability, or waves on the ocean. And in those cases, an active damper is going to not just be a passive material. It's going to be something that's going to be able to respond to conditions a little bit differently. But like you said, cost just continues to go up. So it's really application specific if you need to go to that kind of level.
I think another big common mistake is to think, to overlook actual holes in the wall. You know what I mean? Yeah. Or holes under the door. Like most sound transmission seems to come from those places. Even in the window, little cracks, Like you hear traffic and you think, I'll just put some acoustic treatment around the windowsill. But here, you pull the door and it's really, the door in the studio at the Hart School is, you said it's a 300-pound door, so it's very, very heavy and resistant to vibration transmitting through it. But it also had some suction feeling. It felt like it really was an airtight apparatus.
Even a 1-inch gap at the bottom of a doorway can be as much as 15 plus decibels that you're going to have pass right through. And to your point, that can undermine pretty much anything else at play. And one of the cases where we see it quite a bit, because we do a lot of projects, consulting projects with our sophomore class as well as with our seniors, you go to a space and you can hear what's going on in the adjacent room. One thing that could be happening is the flanking path that goes through one of those types of holes. Another one, which is a little bit sneakier, is going through electrical outlets. The panel cover on electrical outlets, very, very thin. And if we think of sound as having a wavelength, those lower frequency sounds, even 10,000 hertz and below, not really low, but lower in the range, that's going to be a large enough wavelength that it's going to just ignore that. So if you have back-to-back electrical outlets, one room to another, which is a cost-saving mechanism that you might employ, you're going to have sound that goes right through. And so we usually will conduct, a first glance, just kind of use the ears and use a white noise, even just something from a phone. Play that noise, and you can listen for the leaks. If you find those leaks, that's going to get you a long way into solving the problem, particularly if you got a group on a budget. Yes.
HVAC is another one of those sneaky ways that you get in. Everything, all the ductwork in a building is usually tied into one another and sharing one big handler that's moving air to everything. But that's also a way for sound to travel from one place to another. So you have acoustic mouse holes for sound to get through, just not as a degradation of the building, but just in the design of it in the first place. And so when you're designing a space, you really have to take the time to think about all the different ways sound can move from one space into another. And if it's ductwork, it's finding turns, the appropriate number of turns, and calculating the kind of duct you're using, whether it has a dampening of materials inside of the duct, and also the vents that the air flows across as it enters the room can actually vibrate and create its own noise just from air moving across it. So it may not even be that you're getting sound from one room to another. It might just be that you've got someone blowing across a kazoo, basically, in your room, generating rattle and hum, and that's another pain point it's not a cheap fix to, it can be, but it tends to be pretty, once you've solved one problem, sometimes you realize there's lots of others. And that's why home isolation is really difficult, because you don't want to build. If you were to actually build with those sorts of things in mind, you can double, triple the expense of building a home just in trying to address some of these problems.
For me, the anechoic chamber, it kind of makes a lot of sense for a bunch of different tests that could be run, because the idea is that it creates somewhat of a pseudo free field, right? It's the idea being that hopefully most, if not almost all of the sound that you hear from something is direct sound. And that would be akin to like going outside, but also not having the ground, and being really high up in the air, but also not having wind. And, sound goes out, but it never comes back in.
Yeah.
And that's great for testing, like you said, speakers or microphones, and getting the actual data from those things. It's a little bit more confusing to me why someone would build this room, a reverb chamber. Like, what are some actual applications of a reverb?
Yeah, that's a great point. So just like you said, free field conditions are achieved pretty well in an environment like that. In fact, if you did a test, we call it the inverse square law test, you generate some sound. We usually use commercial air purifiers or humidifiers. That's going to make some noise. You measure at one location, you double the distance, you measure it again and double the distance again. Each time you double, you're going to lose 6 decibels of sound, so sound pressure level. If you do that same type of test in a diffuse field environment, which is this reverberation room over here, you're not going to see almost any drop off. So one of the effects, and one of the reasons that a room like this is nice for undergraduates to see and hear, is specifically to see that effect, that you can measure the doubling of distance loss in that free field environment, and then see it's dependent on the field. Diffuse field, you don't get that. It's almost exactly the same level no matter where you are in that space. More practically, like you were saying, why do these kinds of spaces exist? There's a whole ASTM standard for how to design these rooms. So there's plenty of things that people can do with them. One of the main ones that we've done use this room for sound power measurements, and for measurements where you need a lot of diffuse sound. So if you want a sound source that's not necessarily coming from one specific location, that's rather omnipresent, that's coming from all sorts of angles. That way you can test the omnidirectionality of a microphone, for example. We generate all the noise that we can in that space and take the measurements in there. So one of the types of tests that we have done, I did a project with Sikorsky helicopters. We took their helicopter sounds, blasted them over these large Mackie loudspeakers, and then tested the efficacy of several different headsets for pilots. Figure out which of these headsets is going to do best at reducing some of that immense amount of noise. So this is the reverberation room. So if we actually conducted the rest of this video in that room, we're not going to really be able to understand it too well because of all the reverberation. So We'll chat out here. The room is designed to have all acoustically hard materials, floor, walls, and ceiling. So you get at least 95% of all the acoustic energy reflected off of all of those surfaces. So rather than absorbing virtually any of it, everything's going to keep bouncing around until eventually it will die out. Sound is going to persist in there if there are no absorptive surfaces for more than 4 seconds. So a reverberation time of about 4 seconds.
Am I understanding correctly that the difference between that and a regular room would be that in a regular room, you've got the inverse square law and absorption that would attenuate the sound levels, whereas in here, the sound will basically only be attenuated by the inverse square law?
Oh, yeah. Really, air attenuation is the primary factor. So if you didn't have attenuation from air, sound could persist indefinitely, but you're going to get some of it that is absorbed by the air. So after a number of reflections in several seconds, that energy does get completely neutralized. In classrooms, you want to have a specific reverberation time, and that's usually 0.7 seconds or less. Here, a reverberation time of about 4 seconds, several times more than what you'd have. That number is based on good speech intelligibility. So you'd never want to hold a class in that facility.
Now in here, I think we actually could probably have a conversation that would come across in video. All right, but before we do, tell us about what this helps us understand about this room.
Yeah, so this is a Brüel & Kjær Type 2250 sound level analyzer, and it's set to show us what the level is in a space, and it's been calibrated. So we can see from this, the background noise level is about 32 decibels. Talking, we get about 65 decibels. And this is an A-weighted LEQ, so an overall level that's showing us a typical talking environment as well as the background noise. Double doors, as well as a pretty neat design for closing this door. So it opens into the wall, maximizing the space that we have inside. Taking that same measurement in here. So the anechoic chamber, we can see we get about 17 decibels of background noise. That's A-weighted. Talking at about the same level, getting about 58.5 as my A-weighted overall level, my LAEQ.
So unnatural to be in here. First off, I've got some tinnitus that comes out. It's that noise level that I'm used to, I guess, masking that perceptually has disappeared, and you get right a little bit. But not only that, your voice sounds completely different. And I don't know if this comes across on the video. We've got mics and they probably sound very dry. In the past, I've done a video with a binaural head, and that kind of brought it across, but I'll tell you, it's something that I have never felt the exact experience other than actually being inside here. Yeah, I feel like I have the tendency to want to speak louder as well. You feel that too?
Yeah, you get the mix of reactions. You get some people who feel like they need to amplify the voice to compensate for this. You also get other people who come in and the body language kind of shifts, feeling like, oh, I'm making all the noise in this space and I need to kind of crouch and whisper to feel a little bit more comfortable. So kind of see a whole range of different experiences that people have.
I think it would be really cool to see the directionality of any instrument, like you said, the human, move a mic and experiment with that, but also similar to the acoustic guitar miking video that we just made earlier. It seems like a really cool room to understand how sounds radiate from any source, right?
Yeah, and that's what one of the main types of projects we do with a student in here is directionality measurements. Because you don't have any of those reflections, you can determine exactly where the sound is coming from. 2 ways you can do it. One, a rotating boom mic, which we have in the other facility, or by having an array of mics set at different positions, generate a sound. We've done tests with acoustic guitars where students designed an automated picking mechanism. Even though people can be very good at replicating the same level, we wanted even more precision. Maybe less musicality, but more precision on exactly the same force struck each time. And then they generated those directivity plots. Particularly, it was for determining how was the sound going to change when you changed one of the materials on the guitar? Was it going to improve the sound? Was it going to make it so that it spread out more? And we wanted to answer those questions.
Well, that's a project that you and I worked on. We a couple of years ago, trying to find out what is the effect of removing the head of a kick drum versus having a head on the kick drum with no porthole, and then what happens when you put a porthole in the front? How can we measure that? And we used this facility. We made a robotic kick drum pedal, and we used an acoustic camera to measure the sound intensity level of what happens in front of the kick drum head in this room, so that we're sure we're just getting exactly what's coming off the kick drum, and there's no influence of the room whatsoever. And we could find, intensity plots from our results, which ended up becoming an AES paper that we can make some images available for if it's of interest to the viewership.
Awesome.
But that's part of the investigative properties of a scientific study in sound, is you have to remove variables.
Yep.
Right. And so this is one of the most unique places to do research, because you've removed one of the most difficult variables to control for and to understand, because even moving a small inch this way or that way can result in a massive change in acoustics. But when you've eliminated that part, you can really ask some more specific questions and not be influenced by the things around you.
Yep. Yeah, I'm very jealous because I have a scientist at heart, but my bedroom is probably not the most empirical environment to create actual studies. I mean, look at this thing. This is not just like your Amazon.com SPL meter. This is very, very nice. You said it was calibrated. It provides reliable data. Everything about this place is very controlled. Like you said, the intensity, we can get close enough as humans, but if you want it to be really solid data, then you have to control for everything you possibly can, right? That's awesome.
Well, before you leave today, we'll make sure that we get an acoustic guitar in your hands again so you can see what this room sounds like. And we'll do that again in the reverberation room to see the differences between all three environments.
One last thing I wanted to ask. In the video we just made, we discussed the idea of the critical distance, right? I would imagine that in the reverberation room, the critical distance is extremely short. Critical distance meaning the point in the room where the direct sound and indirect sound are at an equal level. Is there even a critical distance possible in this room? I wouldn't imagine, right?
Not really, yeah, because in this case, just like you had mentioned outside, this is a free field environment. So even though we're clearly indoors, almost all the sound that's leaving never comes back. So it replicates that free field environment very well, meaning that, yeah, you couldn't even calculate a critical distance because of that.
And one other thing I'll mention, I guess, is that this is not what I would describe as a perfect room for mixing, right? We often feel that we don't have enough acoustic treatment, but there's a level where there's way too much acoustic treatment. And we've certainly reached that level from a music production standpoint. Maybe not from a scientific research standpoint, but definitely from a listening standpoint. So how do you think we should think about walking that line?
The line between going too far with acoustic treatment?
Mm-hmm. Yeah, between the perfect room for music production, whether it's recording or mixing or even home theater, enjoyment of music and sound, it has to be something between this and the reverb room.
Yeah, well, we want to make sure that when we're doing our mixes, that the sounds that we're reacting to are similar to what someone might experience in their own listening environments. So if you make it entirely dry like this, what you're reacting to and what you're recreating for others is going to only be experienced in a space like this, right? So the idea of a controlled mix facility is one where you're controlling the decay times of relative frequencies across the audible spectrum within the construct of music, right? And the frequencies that musical instruments generate and the way they're performed. And you're doing it in loudspeakers, and the room can give back a little bit and should, because we don't listen to things in a vacuum. We listen to them in au naturel, in the wild, acoustically buck naked, like whatever is in the room is going to be part of the story. And you can't mix in a space that's just like everybody's living room, because we don't all live in the same living room, right? Right, Chris?
Yeah.
So but we can come into a room like this and figure out what are the things and the tools that we utilize that might be influencing our choices in a controlled mix environment, right, that isn't completely dry, it's a way to say, we have these really nice little speakers, these Genelecs, they sound wonderful, but how much of what we're hearing is the Genelec versus what we know to be the original signal, right? And so that gives us a starting point for understanding then what happens when we take that into a not free field environment where we have, boundaries that are going to be reflecting surface information back to us at time delays. So the ideal is to create an even decay time across all frequencies as best you can, with the understanding that we do have some preferences for certain frequencies, and that's the tuning of the room. And tuning is strobe tuners and things for instruments, like that's relative to within a degree of error. There's still a lot of tolerance there, and we still understand that this guitar is in tune, right? And similarly in rooms, you want to be able to tune your room, but you might decide you want a little bit extra low end because you mix, music that benefits from a little bit of extra, artificial help in resonance in the low end. So rooms can be tuned just the way guitars can. And that's not to say you can't modify your own tunings, right? Or invent your own tunings. But in music mix rooms, we're really trying to make the music consistent so that when we make our choices, they're relatable to an average listening experience on the back end, the consumer side, right? And not just making it in this super hyper-controlled imaginarium where you really, like you said, you can't experience it until you walk into it. Yeah. And then there's all these other biological factors that kick in that we don't have when we have normal listening experiences. So yeah, the goal is, you would never want these in your room, but if you had a resonance of say 20 hertz at the back of your room, some of these wedges might be helpful in taming those in those specific areas, right, Chris?
Yeah, and I think that touches on another kind of beautiful aspect of sound and acoustics is that there's subjectivity, and it's quantifiable that there's subjectivity. If I measure 65 decibels A-weighted of background noise, that's an unimpeachable number. It's an accurate number, factory calibrated device. But is that loud? That might be a different answer from one person to the next. And that's why there's going to be preference on different types of room setups. And maybe the best mixing room for one person might not be the best mixing room for another person. So that subjectivity is a pretty fun aspect of studying because, like I said outside, without the human aspect, sound isn't all that we're studying.
One more thing I'll add to this is that in an acoustic design of a mix room, you really want the room to be working in tandem with your loudspeakers. So your loudspeakers perform at certain amplitudes, at certain frequencies. So the idea is to treat your room in such a way that complements the speakers you've chosen for your room. I know some folks who've tried certain speakers in their room that have already been built for other speakers and been like, these sound no good, even though they're very high quality speakers, but they're not going to perform ideally because their curvature profiles are different than the way other high quality, speakers are tuned. And so, the subjectivity is also part of the design, right? The design factor of these loudspeakers. So Genelecs sound wonderful. We could design an entire room based on those Genelecs and then put NS10s in there, and it won't sound as good or as even. And that's because we didn't design a room around the NS10s and their curvatures and their characteristics. So there's no one way to, you can't just kill them all and, have it sound good. The idea is to reinforce the things that need reinforcing or may benefit, and that's a subjective choice to some extent. And then also dampen the things that are maybe a little bit out of control because of the characteristics of the room that you're in, which is just the acoustics of the space, right? The nodes of the space.
Guys, your passion it comes across, and I'm just so thankful for you. Thank you, Chris.
Yeah, thank you.
I could probably sit here and ask you questions all day, but I got to get that guitar in here and do some cool experiments. So the moment you've been waiting for. What were you going to say?
Let's pop some balloons too.
Yeah, true. Let's do it.
Okay.